Hi everyone, welcome back to our operating system course CSC C69. Another video about PintOS. Here we're going to try to understand how PintOS uses the virtual memory. So understanding the virtual memory, of course, is going to be useful for project 3, because in project 3 you're going to be improving the memory management. But it's also useful for project 2, because in project 2, when you do a system call, often you pass pointers as argument of these system calls, and you need to translate the address from a user address to kernel address. Okay? So we're going to look at it a little bit more in detail. So in project 2, this is the view that you have from the user program. Okay? The memory is organized as follows. The code is always loaded at the same address, and the stack always starts at the physical base. And this is going to be true for every user program. And they will never interfere with each other. And that's thanks to the virtual memory. The virtual memory provides some kind of a customized view of the memory to the user program. Okay? And the user program has the kind of the impression that it's running alone in the system. But in practice, actually, this virtual memory is mapped to a physical memory. So let's look at how this works. So in PintOS, the virtual memory layout is divided into pages, and there are two parts. The part about the user space, okay, which is everything below the physical base, and the kernel space, which is everything above the physical base. So for example, here when we allocate the stack, we can access the stack from the user space at the address physical base. But when we do a system call, we can access the same user stack from the kernel space. Okay? But again, this is the virtual memory. So this virtual memory, those pages are mapped to the physical memory. So the physical memory is divided into frame, okay? It's kind of the same idea of the page. And here, every page in the virtual memory maps to a frame in the physical memory. And as you can see here, the user stack actually here in the user space is going to be translated into the same, into the physical address, and here same thing for the kernel space. Okay. So how exactly does this translation work? Well, this is automatic, right? So the CPU is going to do that, and it's going to use for that the memory management unit. But the memory management unit needs to know what's the memory mapping. Okay, so here, for example, when you're in user space, okay, what's the mapping? Well, you know the mapping because thanks to the user page directory. So every process will have a user page directory. And same thing when we are manipulating. Manipulating kernel virtual address, well, there is also a kernel page directory here. And so, depending on which what is currently executing, okay, whether it's the kernel or the program, well, there's going to be a different page directory loaded in the CPU, and the CPU will do the translation. Okay. So let's look at the code a little bit more in detail. So the files that we're going to look at is, of course, process.c, because process.c manage the user program. We're going to look at pagedir.c that actually is going to manage this page directory. And we're going to look at vaddress.h, okay, which actually has some functions that allow us to actually to get the page number if you have a virtual address. It's also gonna we have functions like checking whether the address is whether a virtual address is a user virtual address or a kernel virtual address, and so on. And then we have two important functions here that is going to convert from a virtual address to a physical address and backward. Okay. I'm also going to use this one, although you might not need it in your code. It's pt.h, and this actually going to allow me to deconstruct a virtual address and then use it actually for the translation. You will see. All right, so let's run a little bit of code. Or maybe before we do that, let's look at process.c. So in process.c, first of all, you can see here, when you see, for example, when you load the code, this is in the function load segment, here you can see what's happening. So line 401, this is where we are allocating a page. So here, basically, we are allocating this page here, okay? Or actually, here we are still in the kernel, we're allocating this one over there in the kernel space. And then, as I'm going to explain here, line 414, here we are basically mapping this page here into the user space. Okay? So once this function is executed, well, the code has been loaded. Okay? But also we can see it in setup stack here, where and we're going to look at that into more detail. We're going to trace it into GDB, where we allocate the user stack here in the virtual memory, and then we kind of like install it, meaning we create it in the user space. Okay, so we can see that. And so let's try to trace this code a little bit. So for this video, what I've done is I modified a little bit the make config of PintOS. Okay? And here, line 36, for example, I have added the -G3 flag. This is going to allow me actually to, in GDB, have access to some defined macros, like, for example, physical base. Okay? All right, so let's execute the same program that, the first test case for project 2. So I'm going to run it here. I'm going to modify the command line to have GDB. And also, I'm not going to run QEMU because QEMU is kind of limited. It doesn't give you access to some memory internals, and we need it here. So I'm just going to run it with box. So this is box is the default VM. All right, now let's start PintOS kernel.o. All right, so here, what I'm going to do is, to explain a little bit, I'm going to put a breakpoint on line 437 in process.c. So let's put a breakpoint, process.c, 437. Okay, breakpoint is there. Let's connect to the program. Okay, and let's go to that breakpoint. All right, so here at that stage, what we have done here is we have allocated a page in the kernel space. And here, if I show what's kpage here, that's the address of the page. It's a virtual address of the page in the kernel. So basically, if I look at it here, well, we are here. We have allocated this page here. Eventually, this page is going to host the stack. And as you can see a little bit below here, we're going to initialize the stack pointer for that program to physical base -12. Remember, the -12 is the fix that we put in project 2 to start. Okay. So you might kind of ask, okay, so what is the address here of the stack in the user space? Well, you can ask. So here you say, okay, it's physical base -12. Okay. So here, this is the address, the virtual address of the beginning of the stack, but in the user space. Okay. So this is a user virtual address. So here, okay, so what's this address in the kernel? Okay. It's going to be somewhere around, somewhere in this page here, the page that we have allocated, right? So, well, for that, we can actually translate the user virtual address into a kernel virtual address. And to do that, what we need is, well, as shown here, we need to know the page directory. So here, so first of all, we can see what's the current thread. Okay, oops, I forgot the P. Okay, and here in the current, so the thread that we're executing, it's argnode. Okay, and here in this information, here you can see the page directory. So that's the address of the page directory for that thread. okay, for that kernel thread. So here, what I can do is like I can ask this page directory, okay, what is the and for that I'm going to use page here get page. Okay, so given this the address of the page directory, what is the address of fizbase -12? Okay, and if I do that here, well, I get 0. Why? Well, that's because here at this stage, again, remember we are actually line 437. We have allocated a page, so this page exists in the kernel, but we haven't updated yet the page directory for the user program. Okay, meaning here we don't have this mapping here. This mapping does not exist. We have this one here, but this one doesn't exist. Where do we create this mapping? Well, we're actually doing this mapping a little bit later, actually here in line 439. So let's move on a little bit. I'm going to say next, and here I'm going to execute line 439. Okay, so now I have installed the page, and if I ask the question again, now this time I have the answer. Okay, I know, for example, that fizbase -12 in this user virtual address corresponds to this kernel virtual address. Okay, so here, maybe I can show again this drawing here. No, if the stack starts here at physical base -12, well, this address here is actually this one. Okay, and you can see that it's above physical base, so it's inside the kernel space. Now, what is the physical address? Well, the physical address, where we can ask, we can say, okay, virtual to physical of, well, this one. So here it doesn't matter which one we ask, but here, well, no, it has to be the kernel address. And here, so let's see, this is, I need to force it to be UI'd. Okay, and that's roughly the address of the physical space. So something interesting here. So the user program will always be mapped like that. But how about the kernel space? Well, the kernel space, it turns out that it's actually, you take the, so there's a one-to-one mapping between the kernel and the physical memory. And from the kernel, you can see the entire physical memory, but shifted somehow. As you can see here, when I've converted this kind of kernel address, virtual address, into the physical address, I'm getting almost the same, minus actually the physical base. If actually I take this physical address and I add physical base, I find again this, I find again the same address. So you see here, this entire the entire kernel virtual memory is mapped directly on one-to-one to the physical memory, but just with a shift. Okay. All right. So that's basically in a nutshell how you go from user virtual address to kernel virtual address and then to physical address. Okay. So you might be a little bit confused by now. Okay. It's okay. It's going to take time for you to understand all this stuff, but when you manipulate an address, always ask yourself, what am I manipulating? Is it a user virtual address, a kernel user address, or a physical address? Most of the time, we're not going to manipulate physical address. Okay, we're going to manipulate always virtual addresses, and we have to kind of think about, like, is it a user address or a physical address? A user address or kernel address. All right, so now to go a little bit further, how is this translation happening? And we have seen that in class, but let me again show you this slide. So, of course, to translate from a virtual address to a physical address, we're going to use the page directory. And there's going to be like this PintOS, like every x86 operating system, use this two-level page lookup. So how does it work exactly? Well, the idea here is like, so first of all, you can decompose the virtual address into two pieces. One is going to be the offset, okay, and it's going to be always from 0 to 12 bits. And the rest of the bits are going to be the page. And the idea of getting a mapping from the virtual address to the physical address is to get from the virtual page what is the corresponding physical frame. But here, because we're using two-page lookup, we can again subdivide this kind of page number into two. Okay, one is going to give us access to the directory, page table, and the directory table, and the second one is going to give us access to the page table. So how does it work exactly? So again, here what we have. Let me go back to the code here. So here we have the page table. So I just put it in variable PD here. So this is the address of the page table for the process. So basically here, when we want to resolve what's physical base, here we can use that address. Let me write it again here, but basically we can use that that page table to actually translate into the kernel address, okay? And then later on, of course, to the physical address. But let's see. Let's try to decompose a little bit what's happening here. So of course you can go into, this is what I've done to understand, right? So you can go in the code and look at the code a little bit. So if you look at page get page, okay, this is actually using lookup page, and lookup page is going to do a bunch of kind of extracting values from the address, and then kind of following these arrows here to first find the entry in the directory, in the page directory, and then from them we have the address of the page table, and then from the page table we finally find the physical frame. Okay, so let's try to go through that actually. So here, what we're going to try to translate is this address here. So physical base -12. So the first thing we're going to do actually is we're going to get, and we know the address of the page table. So first we need to get actually what's the index of in the page directory. Okay? And for that we're going to look at the first bits of the virtual address. So luckily we have a function that does that. Here what we can do is we can actually get the page directory number out of this address, and here it's 767. Okay, so that's kind of the index here in this page table. So then what I can do is just a lookup. So if I do a lookup here, I can basically do the following, right? So I can say, okay, from the address of the page table, okay, so from this address here, I'm going to add this index. So here, if I do that, page directory here. So if I do that, then I'm obtaining an address. What's the address? It's the page directory entry, okay, for that address here. Okay, so physical base -12. Okay, so let's take that, and here I'm going to give it a name, and I'm going to call it PD, page directory entry. Okay, so now from this page directory entry, I can get the address of the page table. Okay? And for that, it's actually simple. Here, it's going to be the value here. So if I do this here, what I'm obtaining here now, this is the address of the page table. So here, well, no, actually, no. This is the content of the directory entry. So now, what I can do is the following. So I'm gonna get this table, okay, and for that, I just can call a function actually to give me the page table. So here now, if I do See? Now I have the address of the page table. Okay, so that was actually a physical address. Here I have the kernel address. Okay, so now I have the address of that page table here. So then what I can do is like I can do lookup, but again I need the index, and the index is going to be given by all the bits between 21 and 12. So here, what are those bits? Well, it's going to be, I'm going to use a function called page table number of the same virtual address, and that's going to give me the index. So now I can do the same thing. So I can do a lookup inside this page table. So if I do a lookup inside this page table, I can do that. Okay, so here I have the address of the page table, and now I'm going to add, basically I'm going to jump here, okay, to get the page table entry. So here, I forgot the P. Okay, so now what I have here is the address of the page table entry. Okay, so now that I have the address of this page table entry, I can look at the value of this page table entry, and now this is going to give me basically the page. So here I can do that, right? So now, okay, no, I forgot to actually record this as page table entry. Okay, and now I can basically do that. Okay, so that address here, it's basically, well, that's the kernel, the physical address, almost, right? Because now we have to add the offset. And if I were to add the offset, it would look like this. Okay, so again, I have some function here that's going to give me the offset of that virtual address, right? So maybe here, yeah, I have the PTE. Okay, and here, as you can see, this is the exact same address as this. Okay, so what I've done here is basically I went through like kind of how do we translate a user virtual address into a kernel virtual address. Okay, and for that I need to actually go through the user page directory. Okay, and again I need to find the entry in the page in the user page directory, and once I have the entry, now I need to get the entry in the, once I have the entry, I can know which page table it is. From this page table, I can do a lookup again, and then finally find it's not really the physical address here in our case. It's actually the corresponding kernel virtual address. And now actually from this kernel virtual address, I can actually translate to a physical address. Okay, so that's a little bit how it works in PintOS, right? So here, so for project 2, you can basically use that function here. So when you want to convert a user virtual address into a kernel virtual address, you can just simply use that function. Okay. But now for project 3, well, you need to actually improve the virtual page management, and you will have to actually modify process.c and pagedir.c. Okay. Now the idea is that in the end, what we want to achieve is that here we want to be able to grow the stack. Okay, and we want to be able to also swap. Okay, so when things grow and you don't have room in the physical memory, well, you want to actually swap and push some of this frame here into the disk, right? So that's coming in project 3. All right, I hope, probably you're confused by now, but again, look at it, try to trace it in GDB, and that's it. Good luck. Bye.